For question 15, we have to assume the battery model for the diode. So the voltage is 0.6 volts for each one of the diodes in the following Clipper circuit. So first we need to draw the input and output waveforms on the same graphs, and then also plot the transfer characteristic for each case. So first we have to perform the circuit analysis, right? So let me zoom in a little bit. So first, we know that we have a voltage, a battery model for the diodes, so they would have like a battery here, right? And another battery down here. So I can erase this one here. So here. So this is 0.6. This is also 0.6. Okay. And then we can perform our analysis, right? So let's suppose we have D1 on and D2 is off. Okay, so D1 on, D2 off. In this condition, the voltage at the output, so the D2 is off, the voltage at the output, it's going to be 3 volts plus the 0.6 from the battery model, right? So if we apply a loop analysis just on this single loop here, right, we have that minus VI plus R times I plus 3 volts plus 0.6 volts is equals to 0. So this gives us I equals to VI minus 3.6 volts divided by R. So in order for D1 to be actually on, indeed on, this current should be positive, right? Because then it agrees with the direction of the current that we assumed in the analysis. And for this to be positive, it basically means that VI minus 3.6 needs to be greater than 0. So this means that VI should be greater than 3.6 volts. So this is the first condition. It's the condition where we observe this D1 on and D2 off. Now for the second condition, let's say we have D2 on and D1 off. In this case, the voltage that we are measuring is actually V out equals to minus 5 volts minus 0.6 volts, which is the same as minus 5.6 volts, right? Now in this case, we would have a current flowing in this direction here, right? Let's say we are adopting this direction. So if we apply a loop analysis here, we get minus VI, so let me use red, minus VI, right, plus I times R, minus 5, minus 0.6 equals to 0. And in this case, Ri is equals to Vi plus 5.6 divided by R. Now in this case, if we get a positive value of current, then diode 2 is actually blocking that current, right? Because it doesn't allow current to flow in this direction. So it's only on when the value of the current I is actually negative, which then implies that the current is actually flowing in the opposite direction of the direction of our analysis here in red. So in this case, VI plus 5.6 should be less than 0, right? Because then this would give us a negative value of current, right? So indeed, VI should be less than minus 5.6. Okay. And there's also the condition where none of them are actually on, right? So suppose D1 and D2 are off. Then in this case, if we look at the circuit, there's no current flowing here, there's no current flowing here, there's actually no current flowing through the load or through this R. So the voltage at the output would be exactly the same as the voltage at the input. So in this case, V out would be equals to VI. And there is still a fourth condition where D1 and D2 are on at the same time. Well, let's see if that's possible. If they are all conducting, you agree with me that we would have, suppose we have our ground here, right? So this is 0. Now let's accumulate the potentials from the voltage sources that we have. So we would have first here 0.6, so we are increasing that, so it's 0.6. Then we increase by 3 volts, that would be 3.6. Then we increase by another 5 here, suppose we are doing clockwise. And then we increase again by 0.6, so a total of 9.2 volts. Now between this node, which we accumulated 9.2 volts, and this node here of 0, there is no resistance. There would be like an infinite current flowing like in this closed loop, right? Now, this infinite current, because it would be positive, going in the same direction as our analysis, it would be blocked by both diodes. They wouldn't allow that to happen. So it's not possible that diode 1 and diode 2 are on at the same time in this circuit. So in this case, actually there is no case. We don't need to worry about it because it doesn't happen. So the only important cases are D1 on, D2 off, D2 on, D1 off, and D1 and D2 off at the same time. So we got the values of the voltages, right? So the voltages would be this one here for when VI is greater than 3.6. V0 would be minus 5.6 when VI is less than 5.6. In between 3.6 and minus 5.6, V out is equals to VI. So now let's draw these conditions in the time domain, right? So we have our time here, again 1 period, half of the period. Let's say here's the peak amplitude and the peak is 12. So volt here, minus 12. And there's also some points of interest. So we have 3.6, so let's say 3.6 is around here, and 5 minus 5.6 around here. So let's draw our input. Our input is just a sinusoid. So let's draw a sinusoid here, right? Now the output, if our VI is greater than 3.6, the output is just 3.6. So if it's greater than 3.6, it's just 3.6. If the voltage VI is less than minus 5.6, the output is minus 5.6. So it stays here. Now in between, if it's in between those, so within this region, then V out is just equals to VI. So it's just this one here, and this one here, and this one here, right? So that's our V out. So this is VI, this is V out. Now if you want to plot the relationship VI over V out, so let's VI, here V out, then let's draw the points of interest. So we have minus 12 here, 12 there. That's not correct. So around here minus 5.6, and around here 3.6, right? 3.6. So if VI is less than minus 0.5, it stays at minus 0.5. So let's draw it, minus 0.5 here and 3.6 there. 5.6, sorry. So if the voltage is less than that, it stays at minus 5.6. If the voltage is greater than 3.6, it stays at 3.6. And in between is just the same value as the input. So it should cross the origin here, but that's the plot that we get for this analysis. Okay.